Hello, everybody. I hope you're having a good break. Um, Someone pointed out or asked about their lab this week. So it looks like you guys are doing an electrochemistry lab. We are starting electrochemistry in lecture, but if you have an earlier lab, which is really to say you have a lab before our Thursday lecture, when I think we'll get to this in detail, um, this video will hopefully help you at least complete the lab question. So, electrochemistry is at its core really chemistry done by moving electrons. And you might say, well, Dr. Moore, that's exactly how chemical bonding works. You move electrons and you share them and whatnot. So, electrochemistry is an interesting variant of this where we're physically moving our electrons, uh, specifically, normally between a metal and its cation. So, we're either depositing metals as metallic elements or we're dissolving metals by taking their electrons and making cations. And this is typically mediated by a wire. So our metals are conjoined somehow so that electron transfer can happen along the wire. And if we have electrons moving through a wire, that's electricity. So if you guys have taken physics, it's not gonna hurt. Um, it probably won't be super helpful, but at least you'll know vaguely what currents are. Like current is just the movement of electrons. You'll have an idea of what a voltage is. A voltage is a potential difference, which is, um, if we think about our energy landscape, you have regions of high energy and regions of low energy, and those could correspond to voltages. So, really, voltage is just how much energy difference from the baseline there is. So, if we have a region of high voltage and low voltage, we can move electrons from the high voltage to the low voltage region, which is how these cells work, these voltaic cells. So all a voltaic cell is, and we have a picture here. This is a galvanic cell, I guess, but same, close. They're very similar. I actually need to look up what the difference is because I don't think I could tell you off the top of my head. I thought one of them, maybe the voltaic cell you apply a voltage to make it go, and a galvanic cell you don't have to, but whatever. So we have metals here. So you'll notice we have metallic copper and metallic silver in the diagram. They're labeled the anode and the cathode. We don't get to pick that. It's just the. Let me think about this. Why don't we just look it up? So we have copper anode. That's a copper 2 plus. Yeah. 0.34. And let's find silver on this list. Pretty sure silver will be down here somewhere. No? There's silver chloride. All right, when in doubt, Google. And then we go look at our list. There it is. So we have a positive 0.7. Okay, so it was above it. So your cathode will always be higher on the standard reduction table. We'll get to that in a minute. But you could be asked to identify which metal in a pair of metals would behave as a cathode versus an anode under a given condition. But really, I just want to emphasize here, we don't get to pick these. Like, it looks like these were picked, but that's just not how it is. This is all set up, and they're describing what happens when you set this up. So, also, I apologize. I have a little bit of cold right now. So we take those metals, we attach them with a wire, and we put them in their respective cation solutions. So notice that we have a copper anode in a copper nitrate solution. We have a silver anode in a silver nitrate solution. These do have to be soluble for this to work, I think. Well, silver chloride was there. You'll notice that these are connected by a salt bridge. So the salt bridge usually contains the common anion, so nitrate, 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 all three of those, and a spectator cation. And the point of the salt bridge is to maintain charge. Why do we need to do that? So if we look at the copper electrode, if we go back to our kinetic molecular theory and we ask ourselves what is physically happening at the molecular atomic level of the anode, we would see metallic copper atoms giving up electrons to become Cu2 plus and floating off into solution. So if we were to let this sit for a long time, we would eventually see our copper anode disappear, or we would get to such a high concentration that we can't do the reaction anymore. We'll talk about that too. On the silver side, we'd see the opposite. We'd see ionic silver, cationic silver, Ag plus, coming up to the electrode, the cathode, accepting an electron and depositing itself there as metallic silver. So, two questions. Where are the electrons coming from? Like, if silver's accepting electrons, it has to get them from somewhere. And copper, if it's giving up electrons, they have to go somewhere. So, hopefully, it's kind of intuitive. Oh, okay, those electrons would go from the copper anode over to the silver cathode. And that's what this wire here is for. So, this is just a conductive wire that allows us to move electrons from the anode to the cathode. And again, if you know physics, I've shot this video several times because I keep messing up. So if you know physics, then you probably have been introduced to electricity as a kind of atomic idea. The idea that electricity is just electrons flowing along a conductive metal. And we haven't talked about metal bonding, but basically metal bonds, if we have like copper, I think copper is a common conductive metal. If you have copper atoms, they form this nice lattice through which electrons can move very fluidly from one atom to another. So the whole thing doesn't change because you have ideally the same number of electrons coming in as you have coming out, but they can move through your medium. Whereas non-conductive things, those electrons are fixed to their respective atoms or molecules. So in metal bonds, conductive metal bonds, you have that free movement of electrons across the whole material. And that's what produces conductivity. So here we can move electrons from the copper anode to the silver cathode. So that's where this electron source comes from for silver. This is electron rich over here. This is electron poor. But if we let this run indefinitely, we would actually see a buildup of charge over here, right? If we're moving electrons, we're moving negative charge over here. This would slowly become more negative. This would slowly become more positive. And to counteract that, we have the salt bridge. So if we don't have the salt bridge, this doesn't work because nature really does not like creating charged solutions. But what the salt bridge does is as you move electrons over here, you bring sodium plus over here to counteract that buildup of electrical charge. So Na plus comes over, that positive charge balances out the recruitment of negative charge to the cathode. On the flip side, as you produce more copper, Cu2 plus in the solution, nitrate comes over from the silver side to balance out that charge as well. So that is our 8-minute primer on how a voltaic cell works. I assume you're going to set this up in lab and measure a passive one and then maybe do an active one. Because the flip side of this, and this is called electroplating, is you can add an electrical current to this. So instead of letting it passively move from copper to silver, you could flip it and move electrons from silver to copper and do it in reverse if you apply an external current. So that's cool. That's how we electroplate things. You put something in a solution and you make this run backwards. All right. So on to the matter at hand. You have some question in your lab manual, and obviously I can't answer the question in your lab manual because that would probably not be very honest of me. So instead, we're going to answer a very similar question based off a question in your textbook. So if we go to chapter 17.4 here, example 17.7, we have a question about predicting redox spontaneity under non-standard conditions. And you'll notice in here that we calculate the energy potential of a cell using what is called the Nernst equation. So we need to talk about the Nernst equation first. So we're just going to scroll up. And here we go. Potentials at non-standard conditions in the Nernst equation. I'm sure me reading your textbook to you is boring, but basically we have different forms of the Nernst equation. We'll talk about this energy definition of the Nernst equation, or rather of the thermodynamic. Right, we've done this one. We've done the thermodynamic at equilibrium. We covered that last week. One thing we'll do is we can say, okay, well, delta G we can redefine as negative NFE. That's electrochem stuff we'll cover next week. But the key takeaway here is we have this definition. So this is the full Nernst equation that the energy of the cell is equal to the standard potential of that cell modified by this negative RT over NF times the natural log of Q. So the standard condition, like, if we're looking at non-standard condition, the standard condition is everything is 1 molar at 25 degrees Celsius, 298 Kelvin. If we vary from that, this is where that comes in. So if we have different concentrations, those are going to make their way into Q. If we're at a different temperature, we're going to use this RT. So if you're just looking at example 17.7, this is non-standard concentrations, but actually it's at standard temperature. And down here, they have another version of the Nernst equation. And notice that this one is at standard temperature, 298 K. So if you're at standard temperature, you can use this equation. But if you're not at standard temperature, you can't. So be very careful choosing this equation because you have to be at standard temperature. And if we don't tell you what temperature you are at, you can assume you're at standard temperature. It's close enough. So like here, they don't say. All right. So that is our minute and a half primer on the Nernst equation. Didn't really tell you what it is. We just kind of described what's in here. This N value is the number of moles of electrons transferred. That is described up here. And then F is Faraday's constant. All right. So let's set this up. I have you may notice that this is a Zoom call and I'm recording my Zoom call, and it's entirely because this is the only way I could figure out to share my iPad for free. So we are going to annotate. Oop. Okay, before I annotate, I have to zoom in first. Now we're going to annotate. All right, so if we take our Nernst equation first, where are my annotations? Come on, let's go. So we're going to write out the large version of the Nernst equation, kind of comprehensive one. The energy of our cell is equal to the energy of our cell at standard conditions modified by that RT over NF times the natural log of Q. All right. So we have a couple questions here, probably, hopefully, which is, what is the standard potential of the cell? What is N? What is Q? R and F are constants. T is given to us in the problem. All right. So why don't we start with the potential of the cell? And these can be confusing. So the potential of the cell is the standard potential, and I'm just going to copy from this basically, but the standard reduction potential of the cathode minus the anode. And in order to find those, we have to go to our standard reduction table. So that's this table in 17.3, table 17.1. This gives us all of those reduction potentials. So we want to look up our specific reaction in here. All right, so we have iron 2 plus going to solid iron. And we have cobalt going to cobalt 2 plus. And so let's just locate those. For some reason, my TV behind me is responding to my voice. All right, so here's iron. Remember, our cathode is the one that is making solid. So we're making solid iron. So this is our cathode. negative 0.477. We're going to subtract from that our anode. So our anode is going to be that cobalt, which should be right here. So negative 0.28. What is going on here? Using the TV back there has opened up YouTube. And these are going to have units of volt. And then we just take that difference. We're going to do 0.477 minus 0.28. Technically, it's negative 0.477 minus negative 0.28. So I'm just going to negate this value. I don't like that. Let's start. Negative 0.477 plus 0.28. Did I write it wrong? Yeah, it's 447. It's 447. I'm sure some of you were out there watching, like, oh God, Dr. Moore, you're going to embarrass yourself. You wrote the wrong number down. All right, there we go. So now let's try it again. We have negative 0.447 minus plus 0.28. There we go. 0.167 volts. Technically, this number has two sig figs on it, so we'll keep that in mind, but I don't like to round early. And we'll just denote that. We'll just put a bar on top of that 6 so that we know. All right, so that is the standard reduction potential of the cell, and that's just the difference between our cathode and our anode. And note that that does not matter what the stoichiometric coefficients are here. So in this case, we're transferring 2 electrons in both cases, but that's not important, okay? All that matters when you write these is those reduction potentials. So don't try to correct this yet. We'll come back for that when we modify this equation, right? Because that number makes it in here, doesn't it? All right. So our Q value, that one's pretty standard. That one, our Q is just our products over reactants to some exponent. So this is a heterogeneous system. We have solids, we have aqueous. Solids don't make it into our Q value, so we're just going to use our aqueous. So we have cobalt on top, which is at 0.15 molar. And in the bottom, we have 1.94 molar iron 2 plus. Ooh, the camera followed me there. NVIDIA broadcast, guys. All right. And then we just need a couple other things. So I am going to strongly recommend that. Let me figure if I can just scroll down on my page here. I'm going to strongly recommend that when you're doing electrochem, you use standard units, okay? So that means our R value is going to be 8.314 joules per mole Kelvin. Faraday's constant. This is one we haven't talked about quite yet. It's really just how much charge is there in 1 mole of electrons. So that's going to be 9.4. Sorry, 64. 0.649 times 10 to the 4th joules. Sorry, nope. I guess technically we could probably write somehow. No, we can't. Coulombs per mole. All right, so keep those values in mind. A joule coulomb is equal to a volt. And that's important because we're going to see that. All right, so let's go back to the standard potential of our, the potential of our actual cell now. And that's going to be equal to that standard potential that we found earlier. It's going to be 0.167 negative volts. We're going to subtract from that RT. That's going to be our 8.314 joules per mole Kelvin times our temperature, which has to be in Celsius or Kelvin. So that's going to be 523 Kelvin. That whole thing will be divided by, that is the tiniest. Fascinating. Why do you think it got thinner? Am I just not pushing it right? So we are transferring 2 electrons here. All right. So if we look at our balanced chemical equation, and this will make more sense once we do redox balancing, but basically we're moving 2 electrons from cobalt to iron. And that is our value down here. So we have 2 electrons transferred, and we're going to multiply that by Faraday's constant, which is 9.649 times 10 to the 4th coulombs per mole. And then that whole thing will be times the natural log of Q, which is our 0.15 over 1.94. And when we math that all together, we've already done over here, we get negative 0.11 volts. And remember, I am now rounding it to 2 sig figs because earlier up here we decided we have 2 sig figs from our standard reduction potential. And that's it. That's how we find the standard or the non-standard reduction potential of a cell. So if we're given different amounts, we're given a balanced chemical equation, we can go look up the half reactions there, balance them, substitute in our concentrations, our temperature, our electrons transferred. I do think this scale, so if you have something where like you see like 6 or 12 electrons transferred up here, I do think you have to put that down here. I'll double check that. Hopefully that will not be relevant to your lab, but I don't know. Actually, I think it is relevant. I think in here you have copper 1 nitrate and tin 2, and if you look at this, like you're gonna have to transfer 2 electrons to take care of the tin. So the total electron transfer will still be 2. All right, so I hope that helps. That was 25-ish minutes. So thank you for the time out of your break, and enjoy the rest of it. I will see you guys on Tuesday.